So I'm going to talk about bubbling ocean worlds. As you can see, there are many bubbles on the front page here. So we have some small bubbles here in the ocean, a new album that came out by my favorite artist, Anderson Bach, called Bubblin. I highly recommend it. But I'm talking about ocean worlds today, so this will probably be a planetary talk. By the way, yeah, this is my embarrassing webpage. Also right here, it looks very serious. But when he mixed me with Europa, as Angerhausen said, I actually became another beast called Europosa. So yeah, I used to be part of two bands. One was La Résonance de la Place in Paris, and another was a dance troupe called Bunga. You might get a bingo there. Bunga, which actually means entropy in Hindi. So, yeah, advancing now to 2118. This is going to be sort of a futuristic talk because I'm still doing lots of calculations on this. This is all of the interplanetary missions that have taken place in the past decades since the Voyager space era. And so you can see every little circle that we've taken is a flyby or an orbit of these planets. And so I wanted to ask you guys, which interplanetary bar should host the 2118 Astronomy on Tap? What's the people's choice?
Planet 9!
Planet 9, oh man.
Yeah.
Pluto! Oh, you guys are thinking far beyond. I thought somebody would actually say Mars. Mars is pretty dry, right? In it, it's pretty dry. And so the thing is, after 38 missions, and I respect those missions, they're good, but we learned it's like very dry and you might get really thirsty. And thirsty is what people at Astronomy and Tap don't want to feel like. So I was thinking that if we advance technology in 100 years with hydrogen fusion and maybe desalination technology, that might dare us to go a bit farther. For example, to Jupiter and beyond, as you can see here. So to the gas giants and to these bubbling ocean worlds. So these worlds right here are actually these satellites of Jupiter. So Europa, Ganymede, Callisto, and then there's Titan, and many more. Even around Triton, even around Neptune, the moon Triton has evidence of being bubbling. So here's one little slogan that I came up with, or just a paragraph, just saying that ocean worlds orbiting hydrogen-rich gas giants could be a sustainable future for humanity for a couple of reasons that I might get into later, and it hosts an abode for the genesis of life as we know it, because we think that life started in the ocean itself. Here's an actual diagram of how the solar system's largest ocean worlds compare in size. So you can see that Earth's only ranks number 3 in this list, and all these like tiny moons have more water than the Earth itself, which is kind of interesting, very far away from the sun. Yeah, so why bubbling ocean worlds though? Because bubbles actually tell us that there are ocean worlds. They tell us that there are things coming out of these ocean worlds. Bubbles are actually trapping volatiles, which we can observe later. So the volatiles that Diane actually talked about, all the things on Mercury, the things that might be on the TRAPPIST planets, like Remo was saying, these are the key to understanding these worlds for astronomers. So here's Exhibit A of an ocean world, maybe familiar, some of you. So there's trapped bubbles inside this ocean, which might be carbon dioxide. Another similar ocean world that you might have seen in your life, maybe at this event. So bubbles trapped inside. Oh, that was a bit obvious, but you can see that you have bubbles on top and trapped inside a medium, and the bubbles in the right-hand panel are actually escaping. And so if you have a flyby of a mass spectrometer, it can fly by these bubbles, trap them into the chamber and detect them and determine what kind of bubble is it. Is it a sodium bubble? Is it a water bubble? These are key questions. So going to the bubbling ocean world Europa, Exhibit D, we've got one of Jupiter's Galilean satellites. So there's Io, Europa, Ganymede, and Callisto. They're all tidally locked for all the questions we had for the TRAPPIST planets. They're all just staring at the same side of the planet, the primary body. And this actually creates many interesting effects. One of which is that there's 3 times more water than on Earth inside. And the other effects is that you can see that there's hydrothermal vents inside, ice fractures, ice blocks. Ooh, hydrothermal vents. And and charged particles also. So I'm not going to lie and say you should just go right now to Europa and stand on the surface and take all the radiation and get hit and fry. I think you would die probably in like 10 hours, maybe less, even with the spacesuit on, but it's getting inside the ocean worlds, which is the key. So it has this strong evidence of an extraterrestrial ocean based on these water geyser observations, and I emphasize it's a tough game because, let's see, the best observation we have is a 200-kilometer high plume. This is like stacking Mount Everest 25 times until you get to the top of this geyser. So if you've been to Geneva and you've seen the jet d'eau, it's like 10 times, 100 times higher than that. And it persisted for 7 hours, and the observation was actually based on by the Hubble Space Telescope. So this is a weaker observation, I would say, where you can see these like little streaks, kind of tentative. But the strong observation can be summarized in this movie. So what they actually saw were aurora, like the same kind of northern lights you see if you go to Norway and Scandinavia. And the aurora were in hydrogen, Lyman alpha, and also oxygen. And so that combination was consistent with a 7-hour water plume that then got dissociated by electrons. It's a very radiative environment. And that is our best evidence of these water geysers at Europa. So, strong evidence of this ocean. And anyone know what this image is?
A black smoker.
Black smoker, that's right. It looks blue, but it's still called a black smoker. And this is supposed to be one of the main entropy sources of creating evolution of these complex organic molecules that then created life on Earth. So inside the ocean. So these similar vents that are probably heated to maybe 500 Kelvin, very, very hot temperatures are venting out and going all the way through the ocean and into the sky, which we can observe. So that's a lot of bubble. That's the conclusion. So, right. Another thing is that it just doesn't have to be water. You can we've also detected sodium. This paper by Mike Brown, Twitter name Pluto Killer, because he found all these other dwarf planets and then demoted Pluto. He actually found sodium at Europa for the first time in 1996. And so Europa seems to be shooting out sodium as well. And so this will be a very critical bubble or volatile that we're going to assess in the next part of this. Here's a nice image of Enceladus. This is Saturn's moon, which is shooting out this water vapor geysers. And this is evidence of cryovolcanism, which is bingo. Volcanism that occurs at temperatures below the freezing point. So you would expect it to be too cold, but there's still volcanism. The volatiles would usually freeze, but they're still shooting out this vapor. This is cryovolcanic. And you didn't see that. Never see it. The next topic is something I'm actually working on now, which is molecular oxygen ice bubbles, which is the idea that there's actually O2 trapped inside Europa right now, and we've actually observed this in the visible band. And the idea is, first, it's sputtered. There's a sputtering occurring due to magnetospheric ions. You get that one. So you break up the water molecules, go through this chemical sputtering process, split it into hydrogen, oxygen, and then there's these dangling hydrogen bonds that sort of weakly bind to the molecular oxygen. And then after it's heated, the regolith is heated, you actually diffuse out molecular oxygen into the atmosphere. And so Europa has a tenuous, a very thin molecular oxygen atmosphere, and a cyclone. So these are a different kind of bubbles on ocean worlds. And obviously you guys are breathing nice oxygen in this room, so it's very obvious that it's good for life, even for those small microbes, single-cell organisms. Apparently it's like a nice little storage mechanism for them. They can keep their energy in a nice place. I'm not a biologist, but I think that's how it works. It's apparently very good for evolution and life in general. So we would be happy that this oxygen in the atmosphere would diffuse down into the ocean. Last point is that it's similar to the comet's oxygen, so winding it all the way back to Raphael's talk in the first Astronomy on Tap. 67 PCG is outgassing. It's also having these bingo, outgassing. Outgassing many volatiles and shooting out and so this oxygen mechanism, molecular oxygen mechanism, might be very similar to a comet's. Alright, so finding extrasolar bubbling ocean worlds is part 2 of this talk. Now this is an ongoing project, and extrasolar bubbling worlds would be very tough because these are light years away now. I just told you it's very tough to find water in the solar system. You've got Europa pretty much just like right next door. And now we're seeing maybe we can do this very far away. So essentially, I like this comic because you think you're observing through this nice telescope, but you're really just a man on a ladder with a magnifying glass. And you're looking at these stars. So, okay, maybe these bubbles are endogenic coming from the gas giant. And just so you can see what kind of dirty stuff astronomers look at and have to reduce, this is kind of the data you deal with. This is probably the best, one of the best transmission spectroscopy observations we have, which, that's a big word, but transmission spectroscopy is just like what Ramo showed, transit, you transit in front of the star, but now you have an atmosphere around it, so the light goes through the gas of the atmosphere, and you find out if there's volatiles that are not, or these bubbles that are shooting out. So they actually detected water. These features with these data points kind of fits the model. This is a great fit right here. So then there's also sodium and potassium observations, which is it's kind of bizarre to see around a gas giant for me. So you start thinking, where is the sodium actually coming from? This is a famous exoplanet called 189733b. It's the hardest rendition. Apparently it's known that it's blue, right? For the exoplanet observers here. It's just some scattering effect. So then the question is, okay, where's the sodium coming from? But by the way, yeah, sodium delta. This is what it looks like. Apparently it's very nice. It's a very bright line. It just lights up like a Christmas tree. That's kind of common. Alright, so discovering extrasolar bubbling worlds now. Evidence from an ocean world. The thing is, these things should be rotating. If there is actually a bubbling ocean world that's giving the source of sodium, like Europa, or maybe it's magma, and it's like looks like this maybe, and perhaps it's rotating around a gas giant, which is actually creating a torus, which is sort of like a donut. Bingo. A torus. So a torus is like a donut that would be around this gas giant. And the torus is sourced actually by bubbles that are shooting out of this moon, for example. So this idea, then you've got this very hot ocean world, a magma ocean world, which could be sourcing the sodium and potassium that's already observed at these gas giants. So going back to our solar system, since that was speculative, these are things we actually understand, things that we've actually seen. So you saw a picture of Enceladus gases. I told you that Europa had that 7-hour plume. Triton has evidence of cryovolcanic activity when Voyager 2 flew by it in 1989. And Io just looks like a really, like 5 cheese pizza. Got gorgonzola on it, mozzarella, everything. And that is all due to volcanism. And every time you look at Io, it is exploding. So this is like the best evidence of these magma ocean worlds. And it's actually been modeled and understood all the different kinds of sodium that is shooting off of Io. So the coolest feature I like is the banana cloud. Bingo. So banana cloud is actually a sodium jet that's sort of shooting out and elongated in this banana-like fashion. While it's orbiting, it's actually stretching out, losing angular momentum in the direction of the orbit. And so it sort of makes this banana feature. Also these streams, which are very fast, they just shoot across the entire system. So you've got Jupiter, which is real tiny here. You've got very fast streams of sodium that shoot across. And then you've got a sodium exosphere, which extends to 500 Jupiter radii, which is 50 times bigger than the sun. And that entire feature could be transiting in an extrasolar planet case. Here are real observations with a sodium filter of this torus. So you can see that the sodium features in these clouds are actually rotating around Jupiter. Let's wind that back. And you can see that there's sodium on both sides. Even though the moon is only on one side, you can have sodium on both sides because of these crazy energetic streams. So that could be in the spectra of the observations that we have today. That's and yeah, so is bubbling evidence of volcanism? Is it evidence of volcanoes? This is from which volcano? Can anybody recognize it? Napoli, Pompeii, Vesuvio. So this is Vesuvius, Mount Vesuvius, in 1944 eruption that occurred during World War II. I think it sort of created some entropy during the war. Small volcano, like a kind of entropy that's occurring in Hawaii right now. So these volcanoes actually have many different kinds of products, and the origin of this sodium and potassium actually is salts. That's salts that are shooting out of the volcanoes. They found sodium chloride and potassium chloride, which is wasn't going to be my first guess. That table salt is actually creating all this sodium that you see. So, simplifying this is that these volcanoes though can generate large amounts of neutral sodium and potassium because they are around a gas giant, which is magnetic. So Jupiter has one of the strongest magnetic fields in the solar system, and so since it has this huge magnetosphere, which is maybe less understood or more understood than Mercury's, but still pretty confusing, it actually is slamming all these moons with electrons. And if it slams a volcano with an electron, you can see this like volcanic lightning, it can actually generate these fast streams of sodium. So that's the physics behind it, that you actually, or physical chemistry maybe, that you have actual electrons creating dissociative recombination such that you have fast, very energetic streams of sodium. So that's the origin of table salt. Okay, here's another real observation of a fast stream of ion sodium shooting at Europa. My friend goes out in the field, and again, every time he points his telescope at Io, he just sees these bright streams of sodium. It's always exploding. Okay, so now we need to answer some fundamental questions, because I was telling you about these bubbling ocean worlds that are very far away from the sun, farther than Mars, where Mars is like frozen and dry. So why can there be so much liquid water? So how can there be oceans beyond Earth? So here's the figure from Tarboking et al., Journal of Astrobiology. And it shows the habitable zone here, the familiar one that Raymond also showed.